Okay, so in this, L10b, we're going to be focusing on the control volume and what it is. And it's an incredibly important idea. And the analogy really is that in most of your physics and engineering classes, you work with something called a system, right? And a system really is like a defined, I'm not exactly sure how they define it, but it's like a defined mass. So you work with, so for example, if you're like, okay, I'm working with a problem and the problem is a ball and I want to know where the ball is going to land. Okay, so what you do is you define the system, so you isolate the ball from the rest of the world or the universe or whatever, and you look at the forces on that ball, and so that is your system. Okay, so analogously, in fluids, we work with a control volume. And I want to just define why we don't use a system first. So if we imagine we had some sort of like a problem, let's imagine we had a reservoir or a tank or something. Okay, and here's the tank, and I've got some fluid flowing in from this side, and I've got some fluid flowing in from this side. Okay, and let's suppose I were to do a, let's just make this thing correct, okay? So let's imagine that then I said, okay, well, I want to work with a system, right? So I want to define the fluid that I'm concerned about. So the fluid that I'm concerned about is right here, okay? So let's say, well, this is my system. Okay, what's the problem with using a system? Well, the problem with using a system is this is a defined mass. So a split second later, okay, so that's at time t equals 1, or t equals 0, so t equals t0. Okay, it looks like that. But a split second later, some fluid has come in here, and so now I've got a new control volume that looks, not control volume, a new system, and the new system looks like this. Okay, some fluid has come in on the left, and some fluid has left on the right, so we have to keep track of our original volume. Our original mass, right? So if we use a system, it's going to look like this at, I should have given that a different color. Let's give it a different color. So like right here. Here it is at t equals t, 1. Okay, so it's some later time. And then if I wait an even later time, t equals time 2, right? Maybe it starts to look like, the original mass of fluid now looks like, it's kind of like doing this. And over here, we've got a big, blob of, new fluid coming in that we weren't keeping track of. And I think you can probably, if you look at this, you're like, this is the system approach, right? We don't like that, okay? We don't want to deal with the system approach. What we prefer to do in this case is we would prefer, if my dog would stop whining, okay, we would prefer to do something like this, something that I think hopefully makes more sense to you. Okay, so if we've got a pipe coming in and we've got a pipe coming out, is we want to just look at a volume that does not move. So we want our volume to be like this. Okay, like that. That is our control volume. And it does not change. Okay, and the thing is, what we do is we just keep track of what's coming in or coming out. Okay, so the surface, the edge of the control volume is the control surface. And so basically what we do is we keep track of the mass that crosses the control surface, and we keep track of what crosses the control surface. And then from that we can do a lot of physics. Okay, so it's, so with the system, it's a defined mass. With a control volume, okay, basically the control volume, this is the volume being integrated over. So what we're doing is we can say, well, I know what's going to happen. I know what's going on in this volume because I can just keep track of what goes into it and what leaves it, and then what's inside of it. And then between those three things, I can kind of determine what's going on. And I'll give you a really good example of that in a second. Okay, the control surface, okay, this is the boundary of the control volume. Okay. And then the system, it moves through the control volume. Okay? So the cool thing about this is that the conservation laws, conservation of mass and momentum, or energy, depending on how you want to do it, energy / momentum, whatever you want to call it, okay, apply on a control volume. Okay, which is pretty cool, right? So there's a lot of cool stuff we can do with that. Okay, so I'm going to kind of go over, by the way, before I get too far, the conservation of mass has a special name in fluid mechanics, and we're going to get to that, but the conservation of mass is called continuity, and that'll be the next class. I don't know why they give it this fancy name. And the conservation of energy we usually use as just a momentum. So one possible sign convention for this, and we probably won't use this, but you will see this in some of my solution sets, is it's something like this. Okay, so let's imagine we have flow through a pipe. Okay, so here's the pipe, and it's got whatever kind of weird dimensions it's got. And we decide that this is the control volume that I want to do. Okay. So so if I say this is my control volume, so then one possible sign convention is to look at this and say, okay, well, this is the velocity coming in. So this is U coming in, or V if you prefer, and this is U leaving. Okay, so if you wanted to do Q, okay, in and out, so let's suppose we wanted to do conservation of mass. So you want to say, okay, then what we're doing is we're basically going to take this area right here, okay, and I want to multiply it times this velocity, okay, this velocity here, I'll call it U1 and U2. So this will be area 1 and area 2. Okay, and what we want to do is we want to use those two to do a sign convention. So I'm going to give you two possible sign conventions, okay, and I'm always going to use the second one. Okay, you may use it, and a lot of the equations are written that way. But a lot of times, so the first one is like this. So we look at area. So basically we would say that Q equals basically U dot A, okay, where those are vectors. Okay? So then the A vector, you're kind of like, well, what is the A vector? Well, the A vector clearly can't be up any more than it could be into the board, right? Because it extends in both of those directions. So the A vector is always defined as out. So A is defined this way, as out of your control volume. Out of your control volume. Okay? So in this sign convention, because the U and the A for 1 are in opposite directions, this one gets a negative. Okay? So if I wanted to kind of do this as using this sign convention, I would say, okay, well, Q1 equals, okay, it's going to be U1 times A1, but because they're in opposite signs, it gets a negative sign. Okay, because they're going in opposite directions. Okay, and then Q2, the flow rate at location 2, the volumetric flow rate, that's going to be U1, or U2, excuse me, times A2, but they have the same sign, so it's going to get a positive. Okay, so I can then say, well, if I were doing conservation of mass, I could say, well, all of this, at time t equals 1,000,000 versus, time at t equals 0, it has the same mass in there. So I can say what goes in has to come out. So we can say the sum of the Q's have to equal 0. So then that means that negative U1 A1 equals, we're summing the Q's, okay, plus U2 A2 equals 0. Okay, which means that U1 A1 equals U2 A2. Okay, so what goes in has to leave. Okay? So that's perfectly reasonable. It's not really that complicated, and this is exactly how I would program a computer to do this. However, I'm going to use a separate sign convention that I prefer because it requires a little bit more thinking, but it makes a lot more sense to me. So my sign convention is like this. In equals out plus accumulation. Okay, and it looks like this. Okay, so what goes in? Well, it's whatever the flow rate is in, okay? And then, well, I should note that this is an incompressible fluid. So it's actually the mass flow rate. I should have done that over here, rho. So let me put a rho out here. Okay, Rocky is going crazy, so he's barking. So you're just going to have to ignore him. Equals rho Q out. Okay, so this is the mass flow in equals the mass flow out plus, well, how much accumulated in this particular container? Well, there was no accumulation, right? It had the same amount at all times, so plus 0. Okay, now I note that the fluid is incompressible, so these things go away. And then I say, well, Qn. I'm not going to do any of this with the signs. I took care of the sign by saying that this was a Qn. So by putting it on a certain side of the equal sign. So this becomes U1A1 equals U2A2. And everything in this case is positive. Okay, noting this is the same result. Okay, what we don't do is we don't worry about dot products. I just say, well, Q equals U times A. Okay, and this is the average velocity. The average velocity is just a bar. Okay, and so if I do that, then I don't have to worry about figuring out the signs. I just know that this one's in, so it goes on the left-hand side of the equal sign. This one is out, so it goes on the right-hand equal sign. That's how you're always going to see me do this, okay, because I don't really like doing this any other particular way. All right, so I'm going to try to make this a little bit more clear by doing another example, and this is a real-world example. So, I particularly enjoyed this example. It's one that my professor when I was in college or grad school gave. Okay, the city of Los Angeles diverts water from the watershed of Mono Lake, a lake with no outlet. There was concern about the falling lake surface elevation caused by this diversion. Given the following artificial, so made up, information, calculate the maximum lake depth before and after the diversion under steady state conditions. Okay, so there's a natural inflow of 1.2 times 10 to the 8th cubic meters per year. After the diversion, that gets cut in half. And there's an evaporation of 2.5 meters per year. Okay, assuming the lake basin is a cone with a radius 100 times its depth. All right, so here's California. Just to give you an idea, it's gonna get a little blurry. This isn't the greatest image, but just to give you kind of an idea of where we are in the universe. Okay, so this is kind of the backstory. So here's Mono Lake right here. Here's Los Angeles. Okay, and this is the Sacramento-San Joaquin Delta, which I did my PhD on. It's right over here. There is, generally speaking, a mountain range. Okay, the Sierras run all along here. Okay. Well, maybe they're not unbroken necessarily. And there's some white mountains over here, as they call them. And basically there's a bunch of rivers. The dog is chewing on something very loudly. And there's a bunch of rivers that drain off the backside of these mountains. And they go into Mono Lake. And so this is Mono Lake right here. Okay. And what happened is, Los Angeles has a shortage of water. So what they did is somewhere in here there's a break in these mountains or something. I don't exactly sure how they do it. But basically they said, you know what, we want that water that's coming out of Mono Lake. So what we're going to do is we're going to divert this water before it gets to Mono Lake. We're going to cut it all along here, all this water that's flowing into Mono Lake, and we're going to take it and we're going to pump it down to Los Angeles. Okay, so to give you a better idea, if we look over here, here's Mono Lake. Okay. Here's Yosemite. Okay, so in Yosemite, there's a bunch of creeks. And what's happening is these creeks drain this way. Okay, some of them drain this way and they make it into Mono Lake. I don't know how many there are. But what happens is Mono Lake has no outlet. So typically if you see a lake, you have water that flows in and you have water that flows out. Okay, this is not the case in Mono Lake. There is no water that flows out. So what happens is, and this is kind of an interesting and an important part of this problem, is that each of these water bodies, as they flow into that lake, they have a tiny bit of salt in them, okay, because they just kind of pick it up as they go through the earth or whatever, as they, flow over the land or whatever. They just pick up the tiniest bits of salt, and all that salt ultimately goes into Mono Lake, and it can't leave because the water in Mono Lake evaporates and the salt gets left behind. And so what ends up happening is the water in Mono Lake is hypersaline, so it's saltier than the ocean, and nobody wants it. So Los Angeles doesn't want the water out of the lake itself. So they're not going to pump the water here out of the lake because they don't want it. So to give you an idea of how hypersaline it is, this is a picture of the surface of Mono Lake. Okay? And you see these salty, pyramids that are just kind of coming up out of the water. Okay? And so as the water surface dropped, the salt got left behind and it crystallized. And this is what you got. And so the water in here is saltier than the ocean. Okay, so, I mean, other examples of, this is called a terminal lake. It's got no outlet, okay? So what they did is, instead they said, you know what? We don't want the water that flows into Mono Lake. We want the water before it gets to Mono Lake, because this water has almost no salt in it. And so what we're going to do is we're going to divert all of this water before it gets into Mono Lake. Okay, however, as soon as you do that, the lake itself, the water is evaporating, but now it's got no more water to replace it. So what's going to happen is the surface of the water is going to fall. Okay, so the water now, this water is heading to LA. Okay, and the lake is now losing water, okay, because it's evaporating and it's got nothing to replace it. Okay, so that's the gist of this. Okay, so the city of Los Angeles diverts water from the watershed. Okay, so they're not diverting it from Mono Lake, but they're doing it from the watershed. Okay, so the falling lake surface is a problem. One of the reasons for that is that when the water level gets too low, at one point there was an island in the middle of Mono Lake, and when the water dropped low enough, that island became connected to the land around it, and there were some foxes that came over there and ate all the birds that lived on that island that were not prepared to deal with that. Okay, so anyway, and there's other problems. They end up getting big dust storms and things like that from the fact that the lake is now dry, or mostly dry, or at least a lot drier. Okay, so we're going to assume that going into the lake, we had this much that used to go into the lake, and then they decided to take half of it to LA, and then this is how much evaporates from the lake. So what I want to do here is I'm going to draw this lake, and I've got a little assumption here. Assume the lake basin is a cone with a radius 100 times its depth. So we could do like this, and here's the lake basin. And we've got two things going on. So we got two possibilities. So one thing is the natural inflow. The water surface is here, like that. And then the inflow after the diversion, the water surface is going to be somewhere lower. Okay, we don't really know where. Obviously, this is kind of an idealized situation. It's not a perfect cone. Okay, and so in both of these cases, I'm going to think about this. Here's my control volume. I'm going to draw it in red. Okay, and so it's like this. Okay, that's my control volume. Okay, and now once I've done the control volume, all I need to do is keep track of the things that are crossing the control volume. Okay, and we've got a few things going on here. So we've got the inflow, which is crossing the control volume, the control surface to get into the control volume. So that's the inflow. Okay, and we've got the evaporation, which I don't really know what's a good color for evaporation, but so the evaporation is crossing our control surface. Okay, it's kind of like drawing a free body diagram. Once you do it, the problem is a lot easier. Okay, so then if I want to solve this, what I'm going to do here is I'm going to say, okay, I want to keep track of the mass flow in, I want to keep track of the mass flow out, and I want to keep track of the accumulation of mass. Okay. And so, well, what's flowing in? Well, that's the inflow. Okay, so that's the density of the water times the flow rate in. Okay. What's the outflow? Well, that's going to be the evaporation. Okay, now the evaporation is a little bit complicated, so I'm just going to write down the word evaporation for now. And then plus the accumulation. And so now this one's a little tricky. Like, what's the accumulation in this problem? Well, I'll give you a hint, is we want the maximum lake depth before and after diversion under steady state conditions. So steady state means nothing is changing. So if nothing is changing, then there's no accumulation. Okay, so that's a 0. Okay, so what we're looking for is when this is steady. So when what is flowing in, rho Q in, equals the evaporation. Okay, now I want to do the evaporation as basically a rho times a Q out. Okay, so we're going to call that a flow rate out. Okay, and so that's an interesting flow rate. And so to get that, for this Q in, I'll note that that's given. I know that. It's either this number or this number, depending on which situation I'm solving. But the Q out, so Q's, if we can, we always want them to be just a velocity, or in this case, I guess it's evaporation, so it's a velocity upwards. So it's a V maybe, okay, times an area. Okay, and I don't want to deal with any dot products. I'm just going to, keep it as a positive thing. I'm going to put it where it belongs, which is on the outside of the equal sign. So in this case, well, I know the velocity in this case is essentially this. That's essentially the velocity. Okay, and this area Well, that's kind of what I'm solving for, right? Because if I know the area, I can get the depth, because I know that the radius is 100 times its depth. Okay? So what we're going to do here is I'm going to say rho Q in equals rho. Now the Q out in this case is going to be the evaporation rate. So I don't know what to call that. Maybe we'll just call that E, okay, times the area of the surface, which is going to be pi r squared on 4. Okay, that's pi. Yeah, let's use pi r squared because let's use pi r squared as the area instead of pi d squared over 4. And the reason we're going to do that is because it's given to us as the radius. Okay. So what I want to do is I want to solve this equation, and I want to solve it for r. Noting, okay, the density of the water is the same. Okay. And so now I've got Qn equals all of that business. Okay. So if I put a little square root here, and I do a little math, so we get Qn over, it looks like E pi. Okay, with E being 2.5 meters per year, Qn being, well, it depends on which part of the problem we've got, and then we've got a pi. Okay, so if we do that, we can solve this problem. Okay, and it looks like I didn't write down the answers, which is pretty silly, so give me a second and I'll solve it. Okay, so if we plug these numbers in, okay, so I've got the radius, the natural radius becomes, so if I plug in the natural inflow and the evaporation rate, I get this one right here. If I plug in the diverted, okay, so the diverted case, that's the radius, and then you just divide those by 100, and you get, in this case, we've got 39.1 meters of water. In this case, we've got 26.7 meters of water, depth-wise. Okay, so that's pretty much how we solve this. And this is how I work conservation of mass, okay, or continuity, as it's called in fluid mechanics, okay? I just keep track of what's coming in, what's coming out. I don't use any negative signs unless they're on the accumulation, okay? One thing I will note that I find really interesting about this, so some of you might be going, wait, there's half as much water. Why is this not half as deep, okay? And I'll tell you, and it has to do with the fact that this is a cone. Okay, so the evaporation, so like right here, when the evaporation is the same over the entire surface, okay, look at how much surface area we have. Okay, so in this case, it's the evaporation times this area, so pi r, I don't know, let's call this the r natural squared. Okay, so the evaporation rate times the area over which it's acting. Well, you'll notice that as this thing goes down, okay, that is a smaller loss term. Okay, so we're losing less to evaporation as this thing gets smaller. Okay, so in a natural system, like we could imagine that if you had this thing right here, and let's suppose that steady state condition, the fluid would be, say, here. Well, because we only have enough water coming in to maintain the water elevation here. Well, what happens if, for whatever reason, there's a huge rainstorm and the water level rises? Well, the water level rises, and now it's at a higher elevation. It's deeper, but it's also got a bigger surface area. So what's going to happen? Well, because of that larger surface area, we're going to lose more to evaporation than the inflow can maintain, basically, and we're just going to, and the water level is going to drop, okay, all the way until it gets to this point right here. If, on the other hand, we have a very short-term drought and the water level drops below this, okay, then what's going to happen is there's less evaporation than there is inflow coming in, because now there's a very small surface area. And so what will happen is the surface of the water will slowly kind of come back to this steady state level, okay? And you could use this equation to solve for how it's going to do that, but in that case, there would be an accumulation term because we'd be keeping track of how it accumulates. So in this case, we're only looking for what is the steady state, when it accumulates. When it reaches that steady state. Okay. So this right here, by the way, this is called a steady state. So if you perturb this surface by raising it in some way, if you raise it, it's going to come back to that steady condition. Okay. If you perturb it by lowering it, it's going to bounce back to that steady state condition. Okay. As long as the long-term conditions remain as they are. Okay, I have a paper that I wrote one time on on steady states, elevation of land. So if any of you guys are interested in that, come ask me and we can talk about it. Anyway, so it's about 25 minutes, and that's the end of this one. So a relatively short total lecture. Make sure you can kind of understand the concepts here, because we're going to start playing with this a lot. This continuity is going to be really, 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 really important. Anyway, I'll talk to you guys later. Take care of yourselves. Take care of each other. Let me know how I can help. All right. Hope you have a good one. Okay, bye.